Hello everyone, welcome to the online lectures. Myself Dr. G. Ramesh Reddy, working as Associate Professor in the Department of Electronics and Communication Engineering, St. Martin's Engineering College. So in this session, I would like to discuss about sampling theorem in signal conversion. So here, before we enter into the sampling theorem, where it is applicable actually, what is the context of sampling theorem, we'll like to know. So we know communication is classified based on the type of data transmission, based on the data type transmitted. Communication is classified into analog communication and digital communication. So where analog communication transmits the a continuous time signal only, whereas digital transmission transmits digital data. So when we compare both, digital transmission has many advantages compared to analog communication. So therefore, digital is preferable over analog communication. But coming to the real world signals are of analog in nature. So therefore, uh, if we are able to convert analog signal into digital, then we can gain the advantages of digital transmission. So let us see, like sampling theorem is applicable in analog to digital conversion of the signals. Now coming to outline of our topic. So introduction to sampling theorem and the context in which sampling theorem is applicable, and definition of sampling, and statement of sampling theorem, and along with the conditions what are need to be maintained. Then sampling theorem including two parts, like one is sampling, another is reconstruction of the signal from samples to original signal. And the next is undersampling. The special cases of sampling theorem, as three cases we are going to consider. One is Nyquist sampling, another is undersampling, another third one is oversampling. So and undersampling leads to aliasing. That is the last content of the today's topic. So sampling theorem is playing a vital role in conversion of analog signal into digital. So the first and foremost step that is to be performed is sampling. That means representing a continuous time signal in discrete form, and then quantizing that discrete signal will lead to digital signal. So that's why we are at the transmitter side, like analog signal will be converted into digital, then multiplexing and transmitting uh, into the communication channel, and at the receiver side exactly the reverse procedure has to be performed. That is, digital data has to be converted into analog. So there also we need to maintain the sampling theorem conditions. Okay. Now coming to the context of sampling theorem, why we go for sampling theorem? In order for gaining the advantages of digital transmission, we are going to use the sampling theorem as a bridge between analog signals and digital signals. So most of the real world signals are of analog in nature. Therefore, to gain the advantages, we need to convert that analog signal into digital. And digital communication or digital transmission has advantages over analog communication, such as signal storage, reproducibility, noise immunity, and security, and integrity, and error detection and correction of the signals are also possible. Like any storage device, if you consider, it stores in the form of digital only. Analog signal cannot be stored. So that's the one of the advantage. Then reproducibility, because it has ones and zeros only, so the probability of success or failure, it will be like 50%. So that is one other another advantage. And noise immunity. So noise immunity in the sense, like the withstanding capability of the digital signals against the noise is more compared to analog signals. So like we can be used in ADCs, like analog to digital conversion and digital to analog conversion. So coming to the definition of sampling. So sampling is defined as the process of converting continuous time signal into discrete time signal. So representing a continuous time signal in the discrete samples. at a discrete instance of time, the signal will be represented. That process we are going to call as sampling. Now, coming to the mathematical approach of the sampling theorem, like any continuous time signal can be represented by a continuous summation of impulses. So, any signal like x of t, continuous summation in the sense integral minus infinite to plus infinite, that is the duration of the signal existence. So, into x of t into del of t dt, del of t indicating the impulse signal. So, we can represent any signal, any arbitrary signal with a continuous summation of impulses. So, that property of the impulse signal will enable us to convert continuous time signal to discrete time signal mathematically. So, coming to the statement of sampling theorem. So, sampling theorem states that any band limited signal of finite energy which has no frequency components higher than Fm can be completely described by its samples and recovered back to original signal if the sampling rate maintained Fs is greater than or equal to 2Fm. That means Fs indicating the number of samples taken per second and Fm indicating the maximum frequency of the input signal which we wanted to be converted into digital. Okay. So, the number of samples taken should be minimum of 2 times the maximum frequency of the input signal. So, sampling theorem involves two things. One is sampling, that is conversion from continuous time signal to discrete, and another is the reconstruction of the signal, that involves converting discrete time signal into continuous time signal. So, sampling becomes successful only when we are able to reconstruct the original signal from its samples. That is why the condition mentioned here, it is Fs greater than or equal to 2Fm. This condition is defined based on the reconstruction of the signal. Now, coming to the mathematical approach, how a sampling theorem can be represented mathematically is like a band limited signal of continuous time signal when sampled properly in the sense maintaining the condition, that is Fs greater than or equal to 2Fm. So, in time domain also it can be written. So, Ts less than or equal to 1 by 2Fm, that condition also we can write like in reciprocal. Okay. So, can be sampled, represented as discrete time signals with no loss of information when the sampling Fs is greater than or equal to 2Fm. Now, coming to the train of impulses, how we can mathematically represent sampling theorem is the given signal x of t, if it is multiplied with an impulse. So, if x of t multiplied with del of t, so it will give the value of x of t at t is equal to 0. So, likewise, if you multiply the given signal with a train of impulses, then the sampling can be performed mathematically, it can be representable. So, that is, so representing a sampling signal, this signal, a train of impulses signal, this is called sampling signal, the signal which performs sampling of given signal. So, P of t is equal to summation n is equal to minus infinite to plus infinite del of t minus nt. That means it is a combination of impulses at regular intervals of time t. So, here t indicating the sampling time interval. So, sampling time interval is Ts is less than or equal to 1 by 2Fm, reciprocal of the twice the maximum frequency, that will be the sampling time interval. Now, so the sampled version of the continuous time signal can be represented mathematically as the product of the given signal with a train of impulses. So, if you multiply the input signal with a train of impulses, it will represent the impulses at discrete instance of time. Okay. So, that is, so x of t into p of t, which can be represented as summation minus infinite, n is equal to minus infinite to plus infinite, x of t into del of t minus nt, right? So it is representing the impulses of x of t at discrete in regular intervals of capital T, indicating the sampling time interval. So this is known to be the ideal sampling, where we are using impulses. So existence of impulse is ideal case. So that's why it is called idealized sampling. Now, how we can represent a sequence of impulses? By using a complex Fourier series representation. So, a sequence of impulses can be represented by using a complex Fourier series as, so P of t is equal to summation k is equal to minus infinite to plus infinite C k into e power j k omega naught t, where omega naught is the fundamental frequency of the input signal, so which is given by 2 pi by capital T. So the T indicating the sampling time interval in our sense here. Okay, whereas Ck is the Fourier coefficient, complex exponential Fourier coefficient, so which can be evaluated as Ck is equal to 1 by T into integral minus T by 2 to plus T by 2, that impulse P of t into e power minus j k omega naught t dt. So on evaluating this, so P of t is nothing but del of t itself. So it is impulse signal. So integral of impulse, the area under impulse signal, nothing but 1, and which is going to exist at t is equal to 0, right? So therefore the value of that coefficient, exponential Fourier coefficient, we will get it as 1 by t. So therefore, P of t, now the complex exponential Fourier series representation of given impulse is equal to summation k is equal to minus infinite to plus infinite 1 by t into e power j k omega naught t. So this is train of impulses signal represented by exponential Fourier series. This we are going to substitute in the spectrum of sampled signal. That is, x of sampled signal is equal to product of the train of impulses into the given input signal, right? So we already represented P of t, the train of impulses, with a summation k is equal to minus infinite to plus infinite 1 by t x of t 1 by t into e power j k omega naught t into 1 by t, right? So this is substituting the previous value. So this signal is substituted here in place of P of t. So which is equal to summation 1 by t into x of t e power j k omega naught t. So this is all up to time domain. So in time domain only we have represented. Now how do we convert this into frequency domain? So spectrum in the sense, the frequency domain version of the sampled signal. How do we get? By applying Fourier transform for that. So as a mathematical approach, we are going to apply Fourier transform for this. So on applying Fourier transform for the product of the two signals, like recalling the properties of Fourier transform, linearity and modulation property, we can write the mathematical expression of the sampled signal in frequency domain as, so Fourier transform of P of t into x of t, so which is equal to P of t substituted here, this one. So it is 1 by t into summation Fourier transform of x of t into e power j k omega naught t. So Fourier transform of given signal multiplied with e power j k omega naught t, nothing but, so 1 by t into summation x of e power j omega minus k omega naught. So in fact, so the frequency spectrum of the given signal contains the replicas of the x of e power j omega at regular intervals of omega naught separation. Okay, so that we can see here the original signal is x of t, which is band limited. Band limited in the sense its highest frequency is restricted to FM, beyond which there is no signal. Like it is magnitude of x of e power j omega is equal to 0 for omega greater than b. That means beyond certain cutoff frequency there is no signal existing for that. So if this is the frequency spectrum of input signal, then the sampled version of the signal contains the replicas of x of omega repeating for every omega s, sampled frequency. Okay. So, in the frequency spectrum, it consists of replicas of the frequency spectrum of original signal, right. Now, coming to signal reconstruction, this is a sampled representation. As of now, we have seen how do we extract our original signal from the samples. So, that is called signal reconstruction, extracting the original signal from the discrete samples, right. So, how we can recover, because so mathematically we have seen the spectrum of sampled signal consists of replicas of x of omega. So, if you are able to extract one x of omega, one cycle of x of omega from that, then we can uh, apply inverse Fourier transform for that and we can get the reconstruction possible. So, in fact, since our signal is band limited, right, and noting that the condition maintained as omega s greater than or equal to 2b, right. So, 2 times the maximum frequency. In fact, maximum frequency is b here represented. So, we can use a low pass filter with cutoff frequency is equal to b can be used as a reconstruction filter. A low pass filter with cutoff frequency b can be used, and we allow the sampled signal to pass through a low pass filter with cutoff frequency b, so which will extract only one cycle of x of omega, and for which if you apply inverse Fourier transform, we can reconstruct the original signal. So, here we have represented the frequency spectrum of the sampled signal, and we also extracted the signal by applying a low pass filtering for the given sample spectrum. So, this is the mathematical approach what we have discussed so far. Now, we let's go to the video which represent the free graphical representation of the signal sampling theory. Right. So, coming to the conversion of analog signal into digital signal, now to understand it more clearly, we are going to consider a periodic sine wave. We are going to consider represented mathematically as a sine of 2 pi t plus pi, which is a one-dimensional signal. So, it one-dimensional in the sense as the value of t changes, its value of the x y of t is also changing. Okay. So, for every instance of time, its value also changes. So, that means that so it will have infinite number of values and in between the representation of the given interval, and it is a continuous function of time. So, it can have infinite values. So, there can be like spacing between the successive values can be very minute, and because it is a continuous time representation of the periodic signal which have a single frequency. Now, so it keeps on changing, having infinite values, and in order for storing the signal, so it is very difficult to store that many values in between the given interval, so which has infinite values, but we can restrict to certain maximum number of instances we can store in the signal, so which will be producing the replica of the continuous time signal in the discrete form. Okay. So, we can limit up to certain range of number of values. Now, how often we want to measure the signal, how frequently we want to represent that, how many number of samples required to represent this complete replica of the continuous time signal. So, for this example, we are taken number of samples as 30 samples represented here with 1 hertz frequency. So, it can go down to 20 or 8 or 2 number of samples used to represent. There will be variation if you use more number of samples, more quality of the signal in representing the discrete time. Okay, so therefore, what is the limit and what is the number which one can have? So that is given by Nyquist-Shannon sampling theorem, right? So as we have discussed in the time domain approach, any band limited continuous time signal can be accurately converted into from digital signals when sampled at a rate. So which is equal to twice the maximum frequency, highest frequency of the input signal. Right. So the first part indicating the at what rate, how many number of samples we have to take. So that is minimum of twice the maximum frequency of the input signal. Along with that, there is also one more point mentioned in the Nyquist-Shannon sampling rate. So it is band limited. Given signal should be band limited. So that means its highest frequency is restricted to FM that we have discussed previously. Right. So for the 30 samples frequency 1 Hz, like if you increase the number of samples, the signal quality can increase. Here we are talking about frequency of the signal in Hertz and the sampling rate in number. So frequency component cycles per second that we know already. Sampling rate is the number of samples per second. Right. So both are mentioned in per second. So therefore, it is more or less like frequency or the number of samples per second, the sampling rate, both can be taken for counting the number of samples used per second to represent the given signal. So with less number of samples if we use, so the signal cannot be accurately represented here. So that's why, so minimum of twice the maximum frequency we have to use. So if 20 is the frequency of the original signal, then 40 is the number of samples that we have to take. So this will give us the highest sampling rate. So minimum of twice the maximum frequency which we can use, and further we can also avoid the aliasing effect. So coming back to the special cases of sampling theorem. So original signal, if it is band limited to B frequency, then if it is sufficiently sampled, the first case as Nyquist sampling rate, we are calling it as Fs is equal to 2 times the maximum frequency, where the frequency spectrum will have successive cycles just touching each other. There is no overlap and there is no gap between the successive cycles of this one, original signal. Now, when you take the second case, oversampled, that means there will be a large gap, there will be a gap between the successive cycles of the original signal. Replicas will have a enough spacing, more spacing, so which will lead to the bandwidth effective utilization not going to happen in this case. And the third case as undersampling. So when we use the Fs as less than the 2 times the maximum frequency. So here, if you observe here, the successive cycles will come close to each other and then overlap with each other. So here this condition is going to be failed. In first two cases, what is the condition required? Fs is greater than or equal to 2 times B. So that is satisfied in this case, but third case it is not satisfied. So overlapping happens. So reconstruction becomes very difficult. You cannot extract a one cycle from this. So that's why it is a failure condition. We call this process as aliasing. So aliasing is nothing but overlapping of successive cycles of the signal in the frequency spectrum of sampled signal, known as aliasing. So that means if you can observe graphically here, the cycles are going to be overlap with each other. In order for extracting this one cycle, so it will become difficult from using low pass filter. So aliasing is going to be a problem. To avoid this, we have to use an anti-aliasing filter. Okay. So we can use anti-aliasing filter as a low pass filter. Before performing sampling, we can go for the anti-aliasing filter. That means, in fact, it is a low pass filter with cutoff frequency. So most of the signals are time limited, not band limited. So therefore, before applying sampling theorem, we have to perform low pass filtering for the given signal in order for conversion from continuous to discrete, so that we can avoid aliasing. That is one method of avoiding aliasing effect. One more thing is, definitely the minimum required sampling rate is 2 times the maximum frequency. So therefore, that condition, if it is falling below, this definitely occurs. So that condition also we need to maintain above the Nyquist rate of sampling. Okay. So that's it from my side. So sampling theorem and the applications as in conversion from analog to digital and digital to analog. Okay. And we can conclude from this as, so what is the best sampling rate we can use? So first case is Nyquist rate also difficult. Oversampling consumes more bandwidth, and aliasing occurs when it is undersampled. So what is the best condition we can maintain for the better approximation practically? So practically we have to use Fs slightly greater than the 2 times the maximum frequency, so that there will be a sufficient gap comes between the successive cycles of the frequency spectrum. So therefore, the better way of performing sampling is slightly over the Nyquist rate. So that will give us the representation sampling successful both ways, like performing continuous to discrete and from discrete to continuous. So this will be successful only when sampling rate is taken slightly above the Nyquist rate. So thank you very much. This is about the sampling theorem in signal conversion.